For centuries, Saturn has been the most beautiful planet in our sky, a pale golden sphere wrapped in perfect shimmering rings, a symbol of balance, of elegance, of permanence. But what if those rings are not permanent at all? What if we are living in the briefest moment of Saturn's history, a cosmic accident, a temporary display that will soon disappear? Because Saturn's rings are not solid structures. They are made of billions of icy particles, some as small as grains of sand, others as large as mountains, orbiting in delicate gravitational harmony, and that harmony may be collapsing. Recent data from NASA's Cassini spacecraft reveals something unsettling. Saturn's rings are slowly raining down onto the planet. Tiny particles spiral inward, pulled by gravity and electromagnetic forces. Over time, this ring rain drains material from the system, and the rate might be faster than scientists once believed. Some estimates suggest the rings could vanish in as little as 100 million years. On cosmic timescales, that is almost nothing, which raises a haunting possibility. What if we are witnessing Saturn during the only era in which it even has rings? Were they formed recently? Are they remnants of a shattered moon? And are they already fading away? Tonight, we explore the life and possible death of the most iconic structure in our solar system. Because Saturn may not be timeless, its rings may not be eternal, and we may be watching the final act of one of the most beautiful spectacles in space. This is the story of whether Saturn is losing its rings faster than we thought. When we look at Saturn through a telescope for the first time, the reaction is almost universal. It does not look real. The rings seem too perfect, too geometric, too deliberate, like something engineered rather than formed by nature. A thin, luminous disk slicing through a pale golden world, casting shadows across its cloud tops. But Saturn's rings are not solid structures. They are not rigid disks or cosmic halos frozen in place. They are dynamic, they are fragile, and they are temporary. For centuries, humanity assumed that Saturn's rings had always been there. When Galileo first observed Saturn in 1610, his telescope was too crude to resolve the rings clearly. He described the planet as having ears. Later observations clarified the truth. Saturn was encircled by a thin, flat ring system, unlike anything else in the solar system. But even then, one assumption quietly took hold. The rings must be ancient. They must have formed with Saturn itself over 4.5 billion years ago, during the early formation of the solar system. That assumption felt natural. The rings looked timeless, permanent, stable. Yet modern science has begun to dismantle that idea. Because the more closely we study Saturn's rings, the more they resemble something delicate, something that could not survive unchanged for billions of years. Saturn's rings are made primarily of water ice. Roughly 90 to 95% of their mass is pure ice, with a small fraction of rocky material mixed in. The particles range in size from microscopic grains to chunks the size of houses and even small mountains. Individually, they are harmless. Collectively, they form one of the most spectacular structures in our solar system. But here is the crucial detail. The rings are extremely bright, and brightness tells a story. Over billions of years, dust from micrometeoroids and interplanetary debris constantly rains down on planetary systems. If Saturn's rings were truly ancient, billions of years old, they should appear dark and dirty by now, coated in layers of accumulated cosmic dust. Instead, they are remarkably clean, almost pristine. That brightness suggests youth. Some estimates propose that the rings may be only 100 to 400 million years old, a tiny fraction of Saturn's 4.5 billion year lifetime. If that is true, then something dramatic happened relatively recently in cosmic history. Perhaps a moon wandered too close to Saturn and was torn apart by tidal forces. Perhaps a comet or icy body collided with a satellite, shattering it into fragments. Whatever the cause, The rings may be debris from a catastrophic event, and if they formed recently, they may also be disappearing. This brings us to Cassini. In 1997, NASA launched the Cassini spacecraft on a journey to Saturn. After a 7-year voyage, it arrived in 2004 and began orbiting the ringed planet. For 13 years, Cassini studied Saturn, its moons, and its rings in extraordinary detail. It was Cassini that delivered the most unsettling discovery. Saturn's rings are not static, they are raining down. Particles from the rings are being pulled into Saturn's atmosphere by a process now known as ring rain. This occurs because Saturn's magnetic field interacts with charged particles in the rings. Tiny icy grains become electrically charged by solar radiation and plasma interactions. Once charged, they follow magnetic field lines, spiraling downward into the planet's upper atmosphere. Imagine billions of icy fragments slowly drifting inward, falling like invisible snow. Cassini measured this process directly. The data revealed that between several thousand and tens of thousands of kilograms of ring material fall into Saturn every second. At that rate, calculations suggest that the rings could vanish entirely within 100 million years. In astronomical terms, that is the blink of an eye. If Saturn is 4.5 billion years old and its rings survive only 100 million years more, then we are living in a rare era, one in which the rings exist at all. This idea challenges our sense of permanence, because Saturn without rings would look very different. It would resemble Jupiter, beautiful, yes, but lacking the majestic halo that defines it in our imagination. We might never have called it the most beautiful planet. The question becomes even more fascinating when we consider the mass of the rings. Cassini performed a daring final mission in 2017 known as the Grand Finale. The spacecraft dove between Saturn and its innermost rings, making precise measurements of the planet's gravity. These measurements allowed scientists to estimate the mass of the ring system more accurately than ever before. The result was surprising. The rings are less massive than previously thought. That matters because a lighter ring system would erode faster. A heavier ring system might survive longer. The updated measurements reinforce the idea that the rings are both younger and more fragile than once believed. But is it that simple? Not entirely. Some researchers argue that ring mass may fluctuate over time. Collisions between ring particles can grind material down into smaller grains. Those grains may be lost more easily to Saturn's atmosphere, but larger chunks can also collide and clump together. The rings are dynamic systems, constantly evolving. This means the erosion rate may not be perfectly steady. There could be periods of faster loss and periods of relative stability. Even so, the long-term trend appears clear. The rings are losing material, and they are not being replenished fast enough to balance the loss. Another factor complicates the picture: Saturn's moons. Some of Saturn's inner moons interact gravitationally with the rings. They create gaps, waves, and ripples within the ring structure. These moons can also shepherd ring particles, maintaining sharp edges and preventing material from dispersing too quickly. Without these moons, the rings might spread outward or inward more rapidly. This delicate gravitational choreography keeps the rings structured, but it cannot stop ring rain entirely. Over millions of years, the balance tips and the ice falls. When we zoom out, the broader context becomes even more intriguing. Saturn is not the only planet with rings. Jupiter, Uranus, and Neptune also have ring systems, but none are as bright or massive as Saturn's. Why? One possibility is timing. Perhaps ring systems are common, but temporary. Maybe giant planets occasionally gain rings through catastrophic moon disruptions. Those rings shine brightly for tens or hundreds of millions of years. Then they fade. If that is true, then Saturn's current splendor may be rare. Not because rings are rare, but because ring phases are short-lived. We might be fortunate observers living during the right epoch to witness Saturn in its ringed glory. But fortunate carries an unsettling implication. It suggests that in a distant past, Saturn may have been ringless, and in a distant future, it will be again. The rings that define Saturn today are not eternal. They are transient, they are evolving, and they may already be halfway through their lifespan. So the question remains, is Saturn losing its rings faster than we thought? Cassini's data suggests yes, but the full story is still unfolding, because measuring erosion rates over cosmic timescales from just 13 years of spacecraft data requires careful modeling and cautious interpretation. What seems fast in planetary terms may still span millions of years. Yet even millions of years are brief in the lifespan of a gas giant. In the next part, we will explore how ring rain actually works in detail, and what Cassini's final plunge through Saturn's atmosphere revealed about the invisible snowfall that may one day erase the planet's most iconic feature. If Saturn's rings are disappearing, then the process must be physical, measurable, governed by forces we understand. So, how exactly do rings fall? At first glance, it seems impossible. The rings orbit Saturn at enormous speeds, tens of thousands of kilometers per hour. They are locked in stable gravitational paths. The balance between Saturn's gravity pulling inward and orbital motion carrying particles forward keeps them suspended. So why would they spiral down? The answer lies in something invisible: electricity. Saturn is not just a massive ball of gas. It is a powerful magnetic world. Deep within its interior, metallic hydrogen churns under extreme pressure. This motion generates a strong magnetic field, similar in principle to Earth's, but far more immense. That magnetic field stretches outward into space, forming a magnetosphere that envelops the ring system. Now imagine tiny particles of ice floating within that magnetosphere. When sunlight strikes them, it knocks electrons off their surfaces. Plasma from Saturn's environment bombards them as well. These interactions give the particles an electric charge. Once charged, they no longer move purely under gravity. They begin to respond to Saturn's magnetic field. And this is where things change. Charged particles do not travel in simple circular orbits. They follow magnetic field lines. Those lines curve from space down into Saturn's atmosphere near the poles. Over time, small icy grains can become trapped along these magnetic paths, spiraling inward like snow drifting toward a warm surface. This is ring rain. It is not dramatic. It is not visible in large chunks crashing into the atmosphere. It is subtle. It is slow. But it is constant. Cassini detected it directly by measuring the composition of Saturn's upper atmosphere. Scientists found elevated levels of water-related compounds, oxygen-bearing molecules that should not naturally exist in large amounts in Saturn's hydrogen-rich atmosphere. Where did they come from? From the rings. The icy particles entering the atmosphere vaporize, mixing with Saturn's upper layers, and Cassini measured the rate. The numbers were staggering. In some regions, thousands of kilograms of material were falling into Saturn every second. In others, the flow was even stronger. Over millions of years, that loss accumulates. Imagine a steady drizzle. One drop is insignificant, but over time, even a drizzle can empty a reservoir. The rings are not a solid disk. They are a reservoir of ice, and that reservoir is slowly draining. But ring rain is not the only mechanism at work. There is also orbital spreading. Collisions between ring particles cause them to exchange energy. Some particles move slightly inward, others move outward. This spreading gradually thins the rings and distributes material over wider areas. Gravitational interactions with Saturn's moons further complicate the dynamics. Moons like Mimas, Enceladus, and tiny shepherd moons embedded within the rings exert gravitational tugs that create gaps and waves. These tugs can push particles into unstable paths. Some drift inward, some are ejected outward. The ring system is alive with motion, It is not a static halo. It is a constantly evolving structure shaped by gravity, collisions, and electromagnetic forces. Cassini's final mission, the grand finale, gave us unprecedented insight into these processes. In 2017, the spacecraft performed 22 daring dives between Saturn and its innermost rings. This region had never been explored before. The goal was precise measurement. By flying so close, Cassini could measure Saturn's gravitational pull without interference from the ring mass. This allowed scientists to determine the mass of the rings with greater accuracy, and the mass turned out to be lower than many previous estimates. A lighter ring system means less material overall. Less material means less time before depletion. This reinforced the idea that the rings may be relatively young and may not last much longer in cosmic terms. But there is still uncertainty. Some researchers argue that ring rain rates could vary over time. Solar activity, plasma conditions, and seasonal changes in Saturn's magnetosphere might alter the rate of particle loss. The rings might experience periods of slower erosion. They might stabilize for a while before accelerating again. We are observing them during a tiny window of time. 13 years of Cassini data is extraordinary by human standards, but negligible by planetary ones. We are extrapolating millions of years from a brief snapshot. Even so, the physics is clear. Small charged particles fall, collisions redistribute material, gravitational interactions destabilize orbits, the net flow appears inward, and Saturn is absorbing its rings. The imagery of ring rain sounds poetic, but it is literal. Water ice, once part of a glittering disk, becomes atmospheric vapor. Eventually, that vapor mixes deeper into Saturn's clouds. The material that once reflected sunlight back into space becomes part of the planet itself. In a sense, Saturn is reclaiming what may have once been part of a moon. There is something cyclical about it. If the rings formed from a shattered icy moon, then the remnants are slowly returning home, a temporary halo collapsing back into its source. This leads to a deeper question. If the rings are young, what caused them? One hypothesis suggests that a moon wandered too close to Saturn's Roche limit, the distance within which tidal forces overcome gravitational cohesion. Cross that boundary, and a moon can be torn apart, its fragments spread into orbit, forming a ring. Another possibility is a collision. Perhaps two moons collided, or a comet struck a satellite, scattering debris into orbit. Over time, that debris flattened into the thin disk we see today. Both scenarios imply violence. Saturn's serene beauty may be the aftermath of catastrophe, and if the rings are the product of a single event 100 to 400 million years ago, then their disappearance may simply be the closing chapter of that event. The rings are not permanent fixtures, they are debris with a lifespan. That realization transforms how we see Saturn. Instead of an eternal icon, it becomes a dynamic system caught in mid-evolution. If we could travel forward 200 million years, Saturn might appear as a smooth gas giant with faint, barely visible rings. Similar to Jupiter, the dramatic bands of ice would be gone. Future civilizations, if any existed, might never know Saturn once wore a crown. That possibility carries a strange weight because it means we are living in a special era. An era in which Saturn's rings are bright, thick, and majestic. An era in which the process of their erosion has just been detected. We are witnesses to a planetary transition. That transition is measurable. So, is Saturn losing its rings faster than we thought? The evidence suggests that earlier estimates underestimated the erosion rate. Cassini's data sharpened the picture. The rings are not stable over billions of years. They are temporary, perhaps dramatically so, but there is still room for refinement. Planetary science thrives on iteration. Future missions, perhaps orbiters with more advanced instruments, could measure ring mass more precisely. They could monitor changes over decades. They could test whether ring rain is accelerating. Until then, we are left with a powerful image, a giant planet slowly absorbing its own halo, an invisible snowfall falling from space, and a masterpiece of cosmic beauty that may already be fading. If Saturn's rings are truly temporary, then the most unsettling implication is not simply that they are disappearing. It is that they may not have existed for most of Saturn's history. Imagine Saturn 4 billion years ago. The young sun was brighter and more violent. The early solar system was chaotic, filled with collisions, migrating planets, and scattered debris. Jupiter and Saturn were still settling into their present orbits. Moons were forming. Some were being destroyed. In that era, Saturn may have been ringless, just a massive gas giant with swirling cloud bands and a retinue of icy moons. No shimmering halo, no thin disk reflecting sunlight like a cosmic mirror. For billions of years, it may have looked ordinary. If the rings formed only a few 100 million years ago, then Saturn has spent more than 90% of its lifetime without them. That thought reshapes the way we interpret planetary beauty, because what we consider Saturn's defining feature may actually be a fleeting accessory. So, how do rings form? To understand their possible youth, we need to understand the mechanisms capable of creating them. The first concept is the Roche limit. Every planet exerts tidal forces on nearby objects. These forces arise because gravity pulls more strongly on the near side of a moon than on the far side. If a moon ventures too close to its planet, those tidal forces can exceed the moon's own gravitational cohesion. When that happens, the moon cannot hold itself together. It fractures, it shatters, and its fragments spread into orbit. For Saturn, the Roche limit lies just inside the current ring system. If a moon migrated inward, perhaps due to gravitational interactions with other moons, it could have crossed this boundary and been torn apart. The resulting debris would not immediately form a flat disk. At first, it would be chaotic, fragments following varied trajectories, but over time, collisions between pieces would dampen their vertical motion. The debris would settle into a thin equatorial plane orbiting Saturn in a disk. That disk would become rings. There is supporting evidence for this scenario. Saturn's rings are composed primarily of water ice, the same material that makes up many of its moons. If the rings were remnants of a shattered icy satellite, their composition would match, and it does. But there is a complication. The rings appear remarkably pure. They contain far less rocky material than expected. If they were simply the remains of an ordinary moon, this suggests that if a moon was destroyed, it may have been differentiated, with a rocky core and icy outer layers. Perhaps only the icy mantle was dispersed into rings, while the rocky core fell inward or remained intact. Another hypothesis proposes a different origin. Instead of a moon crossing the Roche limit, perhaps a large comet or Kuiper belt object collided with a moon, shattering it into fragments. Such collisions were more common in the early solar system, but they still occur, albeit rarely. A catastrophic impact could have scattered enough material to form the rings we see today. Both scenarios imply violence. Saturn's rings may be the aftermath of destruction, and if they formed only a few 100 million years ago, then they represent a relatively recent event. But how do we determine their age? Brightness, micrometeoroid bombardment, mass. These are the clues scientists use. Interplanetary dust constantly drifts through the solar system. Tiny particles collide with ring material, embedding themselves and darkening the ice. Over billions of years, this should accumulate significantly. Yet Saturn's rings remain strikingly bright. Models of dust accumulation suggest that if the rings were billions of years old, they would appear much darker. This supports a younger age. Cassini's mass measurements also matter. A lighter ring system would accumulate dust faster relative to its mass, darkening more quickly. If the rings are both light and bright, then they likely have not been exposed to dust for very long. This convergence of evidence, brightness and low mass, strengthens the youth hypothesis. But youth introduces a paradox. If ring formation events are rare, then observing Saturn during such a ring phase seems unlikely. Statistically, we should be more likely to see Saturn without rings. Unless ring formation events are not rare, perhaps ring cycles occur multiple times during a planet's lifetime. Moons form, moons migrate, moons break apart, rings form, rings dissipate, and the cycle repeats. In this view, Saturn's rings are not a singular event but one chapter in an ongoing process. This possibility changes the narrative from tragic loss to dynamic renewal. The rings may vanish, but future rings could form. Planetary systems are not static sculptures, they are evolving ecosystems governed by gravity. To understand this evolution, scientists model the orbital dynamics of Saturn's moons. Tidal interactions between Saturn and its satellites cause moons to gradually migrate outward over time. This is similar to how Earth's moon is slowly drifting away from us. But in complex multi-moon systems like Saturn's, gravitational resonances can cause orbital instabilities. Moons can shift positions, their orbits can change. In rare cases, these changes might push a moon inward instead of outward. If that inward migration carries it past the Roche limit, destruction becomes inevitable. In this framework, ring formation could be an occasional but natural outcome of long-term orbital evolution. Cassini provided additional hints about ring structure that support ongoing evolution. Within the rings, waves ripple outward from gravitational disturbances caused by moons. Spiral density waves and bending waves reveal subtle interactions. These patterns are not static, they evolve, they shift. They demonstrate that the ring system is highly responsive to gravitational forces. The rings are not a frozen snapshot of a past event, they are an active system, which means their eventual disappearance is not sudden. It is gradual. The loss of ring material through ring rain and orbital spreading does not erase the rings overnight. Instead, they thin, they fade, they become less dense. Over tens of millions of years, the bright bands may become faint streaks. Eventually, they may be barely visible. Saturn, without prominent rings, would still have a magnetosphere, still have moons, still have storms, but its visual identity would change. The irony is striking. The planet that appears most permanent may be the most transient in appearance. This realization also challenges how we define planetary identity. When we say Saturn, we immediately imagine rings, but perhaps Saturn's ringed phase is just one aesthetic period in a much longer history. If intelligent observers had existed 1 billion years ago, they might have described Saturn differently. If intelligent observers exist 1 billion years from now, they might see a ringless gas giant. We are observers at a particular moment, and that moment may be rare. So when we ask whether Saturn is losing its rings faster than we thought, the deeper question is this: were we wrong about their permanence from the beginning? The answer appears to be yes. The rings are not ancient fixtures. They are dynamic debris. They are evolving structures shaped by physics, and their lifespan, whether 100 million years or several hundred million, is short compared to Saturn's age. That does not make them insignificant. In fact, it makes them extraordinary, because we are witnessing a temporary cosmic masterpiece, and temporary beauty carries its own kind of weight. In the next part, we will explore how Saturn's moons influence the rings and whether they might slow, reshape, or even accelerate the disappearance of the most iconic feature in our solar system. Saturn's rings do not exist in isolation. They are not a static halo suspended in emptiness. They are embedded within a complex gravitational system, one shaped by more than 80 moons, each exerting its own subtle influence. To understand whether Saturn is losing its rings faster than we thought, we must understand the role of these moons, because the same forces that maintain the rings may also contribute to their erosion. At first glance, Saturn's ring system appears sharply defined. Distinct bands, the A ring, The B ring, the C ring, dark gaps like the Cassini Division, cutting cleanly between them. Thin, intricate structures carved with precision. But these features are not permanent lines etched into space. They are maintained by gravitational choreography. Consider Mimas, one of Saturn's larger inner moons. Mimas orbits just outside the Cassini Division. Its gravitational pull creates a resonance within the rings. Particles orbiting at certain distances complete exactly 2 orbits for every 1 orbit of Mimas. This repetitive gravitational tug clears out material, carving the Cassini Division. Without Mimas, the gap would gradually fill. The rings would blur. Now consider the tiny shepherd moons embedded within the rings themselves. Moons like Pan and Daphnis are small, only tens of kilometers across, but they play a powerful role as they orbit within gaps in the rings. Their gravity confines nearby particles, maintaining sharp edges. They act like invisible hands, holding the rings in place. But shepherding is not a neutral process. When a moon interacts gravitationally with ring particles, it transfers angular momentum. Some particles gain energy and move outward, others lose energy and drift inward. These exchanges create waves, spiral density waves, that ripple through the rings like patterns in a vinyl record. Cassini photographed these waves in exquisite detail. They are evidence of constant motion, constant exchange, and exchange means change. Over long timescales, these interactions can redistribute material within the ring system. Particles pushed outward may spread into thinner regions. Particles pushed inward may approach Saturn's atmosphere. The rings are not a closed system. They are influenced by every moon that orbits nearby. Then there are tidal interactions. Saturn's gravity stretches its moons, generating internal heat. This process is responsible for the geological activity of moons like Enceladus, but tides work in both directions. Moons also exert tidal forces on Saturn. These mutual interactions cause gradual orbital migration. Most of Saturn's major moons are slowly drifting outward. This outward migration changes gravitational resonances over time. Resonances that once stabilized, certain ring regions may weaken. New resonances may emerge. The structure of the rings evolves accordingly. If a resonance shifts, ring particles previously held in stable orbits might become unstable. Instability can mean spreading or inward drift. Over millions of years, even tiny changes accumulate. There is also the question of mass transfer. Enceladus, for example, emits plumes of water vapor and ice from its south pole. Some of this material feeds Saturn's E-ring, a faint, diffuse ring extending far beyond the main ring system. In this case, a moon is replenishing a ring, but the E-ring is much more tenuous than the main rings. There is no known moon currently replenishing the dense A and B rings at a significant rate. If they are losing material, there is no obvious source replacing it. This imbalance matters. A ring system that loses more than it gains will eventually fade. Even if moons sculpt and shape the rings, they cannot stop overall mass loss. If the dominant processes favor erosion, Cassini's observations revealed another layer of complexity. Electromagnetic forces interact not only with ring particles, but also with plasma generated by Saturn's moons. Charged particles from volcanic activity on Enceladus, for example, populate Saturn's magnetosphere. These particles can collide with ring grains, altering their charge states and influencing their motion. The rings exist within a dynamic plasma environment. This environment can enhance ring rain under certain conditions. If plasma density increases, charging effects may strengthen, accelerating the inward spiral of small particles. Thus, the moons indirectly influence erosion through their contribution to Saturn's magnetospheric environment. There is also the possibility of moon-ring collisions. While large moons orbit outside the main rings, smaller moonlets embedded within the rings occasionally collide with ring particles. These collisions can fragment material into finer grains. Finer grains are more susceptible to electromagnetic forces. which means they are more likely to fall into Saturn. In this way, collisions within the rings may indirectly increase ring rain rates. A cascade effect. Large chunks break into smaller pieces. Smaller pieces fall faster. Over millions of years, this gradual grinding could significantly thin the rings. Yet paradoxically, collisions can also cause clumping. Ring particles occasionally stick together, forming temporary aggregates. These aggregates may grow to tens or hundreds of meters in size before being torn apart by tidal forces. This constant cycle of aggregation and fragmentation adds to the dynamic complexity of the system. The rings are not uniform sheets, they are granular systems behaving almost like fluids under gravity. Fluid systems evolve, they redistribute mass, they dissipate energy, all of which influences their lifespan. Another subtle influence comes from Saturn's seasonal tilt. Saturn is tilted by about 27 degrees relative to its orbit around the Sun. Similar to Earth's tilt, as Saturn moves along its 29.5-year orbit, sunlight strikes the rings at varying angles. During equinox, the rings are illuminated edge-on. During solstice, they are fully lit from above or below. These seasonal changes affect ring temperature. Temperature affects particle charging and plasma interactions. While seasonal variations do not determine the ultimate fate of the rings, they modulate the processes that contribute to erosion. The system is intricate, it is interconnected, and it is constantly shifting. When we step back, a pattern emerges. Saturn's rings are maintained by moons, but they are also destabilized by moons. They are shaped by gravity, but gravity also spreads them. They are influenced by electromagnetic forces, but those forces also drain them. It is not a simple story of destruction. It is a story of balance, gradually tipping. The moons act as sculptors, carving, shepherding, maintaining structure, yet they cannot prevent the long-term loss of material. The ring system appears to be in a slow decline, not a collapse, not a sudden disappearance, but a gradual thinning that will continue unless a new catastrophic event intervenes. And that possibility remains. If Saturn's moons continue migrating, orbital resonances could eventually destabilize another moon. Perhaps one will wander inward, cross the Roche limit, and be torn apart. A new ring system could form. If so, Saturn's ring phases might be episodic, separated by long intervals of relative emptiness. We may simply be witnessing one such phase. The presence of shepherd moons and resonances does not guarantee permanence. It only shapes the timeline. So when we ask whether Saturn is losing its rings faster than we thought, we must account for this entire gravitational ecosystem. Cassini gave us a snapshot, but the story spans millions of years. The rings are sculpted by moons, fed by occasional debris, drained by ring rain, spread by collisions, and shaped by magnetism. The cumulative effect appears to favor loss over gain, which means Saturn's crown is not eternal. It is sustained by delicate forces that over time cannot overcome erosion. In the next part, we will explore what Saturn would look like without its rings, and how their disappearance would alter not just its appearance, but its identity within the solar system. If Saturn's rings are truly temporary, then we are faced with a strange and almost uncomfortable thought. What would Saturn look like without them? For most of human history, Saturn has meant rings. The two are inseparable in our imagination, in textbooks, in artwork, in telescopes pointed into the night sky. Saturn's identity is its halo. Remove the rings, and something feels missing, as if you've taken the crown from a king. But physically, Saturn is still a gas giant, massive, turbulent, complex. The rings are an accessory. Spectacular, yes, but not essential to the planet's existence. Without rings, Saturn would resemble a slightly smaller version of Jupiter. Its cloud bands would dominate the view, subtle stripes of cream, gold, and pale brown would wrap around the planet. Massive storms would still churn within its upper atmosphere. The hexagonal jet stream at its north pole would remain, one of the strangest atmospheric features in the solar system. But from a distance, Saturn would no longer stand apart. Jupiter would likely reclaim the title of most visually striking gas giant. Saturn would become another striped sphere. This visual transformation has implications beyond aesthetics. Planetary rings affect how sunlight reflects off a planet. They increase overall brightness. In telescopic observations from afar, even from outside our solar system, a ringed Saturn would appear brighter and potentially larger than a ringless one. Astronomers studying distant exoplanets sometimes look for brightness variations that could hint at rings. Saturn's rings dramatically increase the area reflecting sunlight. Remove them, and Saturn's albedo would change. This means that if Saturn lost its rings, its detectability from afar might suddenly shift. Now imagine the long-term process. The rings would not vanish in a dramatic event. They would thin over tens of millions of years. The dense B ring, currently the brightest and most massive, would lose material. Gaps would widen. Particles would spiral inward. From a distant telescope, the rings might first appear less distinct. Eventually, only faint streaks would remain, similar to the thin ring systems of Uranus and Neptune, and then perhaps nothing obvious at all. Saturn would look naked. There is a psychological element to this change. We assume planetary features are permanent because our lifetimes are short. A mountain seems eternal. A continent seems fixed. A planet's rings feel unchanging. But planetary systems evolve constantly, just slowly. If intelligent beings had observed Earth 1 billion years ago, they would have seen a very different world. Continents in different positions, a different atmosphere, no complex life. Likewise, Saturn's current appearance is a snapshot in time. The idea that we might be witnessing the final 100 million years of its ring phase is humbling, because 100 million years is nothing astronomically, but vast compared to human history. Human civilization has existed for perhaps 10,000 years. If the rings last another 100 million years, they will outlive our species many times over. Yet they remain temporary. The disappearance of Saturn's rings would also affect its moons. The rings and inner moons exist in gravitational interplay. Remove the rings, and orbital resonances might shift. The distribution of mass around Saturn would change slightly. These effects would be subtle, but over long timescales, small gravitational adjustments matter. Even Saturn's atmosphere might respond. Ring rain currently deposits water and oxygen-bearing compounds into the upper atmosphere. If the rings fade, that influx would diminish. The chemistry of Saturn's upper atmosphere could gradually shift as a result. A planet's appearance is not separate from its physics. They are intertwined. Now consider a broader cosmic perspective. Our rings are unusual. All 4 gas giants in our solar system have ring systems. Jupiter's rings are faint and dusty. Uranus has narrow, dark rings. Neptune's rings are clumpy and incomplete. Saturn's are simply the most massive and reflective. This suggests that rings may be common phases for giant planets. Perhaps every gas giant cycles through ring formation and ring loss over billions of years. If so, Saturn's current brilliance is not unique, just currently visible. In the distant future, perhaps Uranus or Neptune might acquire more massive rings. Perhaps Jupiter once had bright rings long ago. The solar system is dynamic. What seems permanent is often temporary. But Saturn's rings are more than a physical feature. They are symbolic. They represent balance, a thin structure orbiting a massive planet, held in place by gravity and motion. They are a reminder of how delicate stability can be, and their slow disappearance would represent a shift in the visual character of our solar system. If we imagine humanity thousands of years in the future, still observing Saturn through telescopes, They might record gradual changes. Perhaps ancient records would show thicker rings, future records would show thinner ones. The realization that the rings are fading would become part of Saturn's story. But here is another possibility. What if Saturn's rings are not nearing the end of their life, but closer to the middle? Some models suggest that ring rain rates might decrease as the rings thin. Fewer small particles would mean less charging and less inward spiral. In that case, erosion could slow over time. The rings might persist longer than 100 million years. Estimates vary because the system is complex, and complexity breeds uncertainty. Cassini gave us unprecedented data, but even Cassini's measurements represent a short observational window. Long-term monitoring over centuries would provide clearer answers, but we do not yet have that timescale, so we exist in uncertainty. The best evidence suggests that Saturn's rings are temporary and gradually disappearing, but the exact timeline remains debated, and that uncertainty adds depth to the story. We are not witnessing a sudden collapse. We are studying a slow evolution, a planetary accessory fading at a pace too slow to perceive in a single lifetime, yet fast in cosmic terms. There is a strange beauty in that, because it reminds us that change governs everything in the universe. Stars evolve, galaxies collide, moons migrate, rings fade. Nothing is frozen in permanence. Even the most iconic structures are temporary arrangements of matter and energy. If Saturn loses its rings, it will not lose its identity as a gas giant, but it will lose the feature that defines it to us, and perhaps that makes our era special. We live during the ringed epoch of Saturn, a chapter that will one day close. In the next part, we will explore how scientists estimate the remaining lifespan of the rings, and whether new data could dramatically change the timeline we currently accept. If Saturn's rings are fading, the most important question becomes simple, but incredibly difficult to answer. How long do they have left? It sounds like a countdown, a cosmic timer, slowly ticking down toward invisibility. But estimating the lifespan of something as vast and complex as Saturn's rings requires us to combine physics, observation, modeling, and a large amount of uncertainty. Cassini provided the first serious constraint. Before Cassini, estimates of ring age ranged wildly, from billions of years to a few 100 million. Some scientists believed the rings formed alongside Saturn itself. Others suspected a more recent origin. Cassini changed the conversation by measuring the mass of the rings more precisely, and by directly observing ring rain. Scientists were finally able to connect two critical numbers: total mass and mass loss rate. When you divide the first by the second, you get a rough estimate of lifespan, and that estimate suggested something surprising. If ring rain continues at the measured rate, Saturn's rings could disappear in roughly 100 million years. Some models extend that to perhaps 200 or 300 million years, but even the upper estimates place the lifespan well under 1 billion years. That means the rings are likely less than 10% as old as Saturn itself. But here is where the story becomes more complicated. Mass loss is not necessarily constant. Cassini observed ring rain during a specific window of time, roughly 13 years. But Saturn's magnetosphere changes, solar activity changes, plasma density changes, ring particle size distribution changes. If the environment shifts, the erosion rate could accelerate or slow down. So the estimate of 100 million years is not a guaranteed expiration date. It is a projection based on present conditions. Think of it like measuring the melting rate of a glacier over a decade and projecting its disappearance. The projection is valid only if conditions remain similar. Planetary systems rarely remain static. There is also another factor: particle size. Small particles are more vulnerable to electromagnetic forces. They are more easily charged and more easily dragged along magnetic field lines towards Saturn. Larger chunks, some meters or even tens of meters across, are far less affected. If the rings gradually lose their smallest grains first, the erosion rate might slow over time. In that scenario, the rings would thin but persist longer than expected. Alternatively, collisions within the rings could grind larger chunks into smaller grains, increasing the fraction of vulnerable particles and accelerating loss. Which of these processes dominates? That remains uncertain. Models attempt to simulate millions of years of ring evolution, but even small assumptions can change the outcome dramatically. Then there is micrometeoroid bombardment. Dust from the outer solar system constantly strikes the rings. These impacts darken the ice and alter its composition. Over time, accumulated contamination should make the rings less reflective. If the rings were billions of years old, they would likely be much darker. Their brightness supports a youth hypothesis, but dust accumulation also slightly increases ring mass, at least temporarily, before collisions redistribute or eject material. The balance between contamination, erosion, and redistribution is delicate. Now imagine projecting forward 100 million years. The B ring, currently the most massive and dense, would gradually thin. The Cassini Division might widen. The A ring might lose its crisp edge. From a distant viewpoint, the rings might still exist, but fainter, less dramatic. After 200 million years, perhaps only tenuous streaks would remain. Eventually, only a faint halo like Jupiter's would persist. But what if the loss rate increases unexpectedly? Saturn's magnetosphere is influenced by the solar wind. As the sun evolves over billions of years, its output will change. In the distant future, the sun will brighten significantly. That increased radiation could alter charging processes within the rings. More charging could mean faster ring rain. Additionally, gravitational resonances among Saturn's moons could shift. If a resonance destabilizes a moonlet within the rings, it could fragment into smaller pieces, increasing erosion temporarily. So the future of the rings depends not just on current loss rates, but on the evolving dynamics of the entire Saturn system. There's also a philosophical dimension to this question. When we say disappear, what do we mean? Will Saturn suddenly look empty, or will the rings gradually become too faint to notice? The disappearance will not be a dramatic event visible in a single generation. It will be a fading, a slow erasure. And from a purely scientific perspective, that fading is part of planetary evolution. Rings are not permanent features. They are outcomes of gravitational accidents, temporary configurations of debris orbiting a massive body. If Saturn's rings formed from a destroyed moon, then their eventual disappearance simply completes the cycle. Matter returns to the planet, energy dissipates, equilibrium shifts, but there is still one wild card. What if another moon crosses the Roche limit? What if millions of years from now, orbital resonances push an icy satellite too close to Saturn? A new ring system could form. Bright, massive, fresh. In that case, Saturn's rings would not be a one-time event, but a recurring phase. This possibility challenges the idea that we are witnessing the final era of rings. We might simply be witnessing one ring epoch among several. Planetary systems often surprise us. Cassini itself revealed unexpected phenomena: hexagonal storms, water geysers on Enceladus, lakes of methane on Titan. The solar system is far more dynamic than we once believed. So while current evidence suggests Saturn is losing its rings and likely will continue to do so, the long-term story may include renewal. For now, the data points in one direction. Ring rain is real. Mass loss is measurable. The rings are younger than Saturn, and their future is finite. But finite does not mean immediate. Even 100 million years is an immense stretch of time, longer than the time since the dinosaurs went extinct, longer than mammals have dominated Earth, longer than most planetary features on Earth, have remained unchanged. So when we ask whether Saturn is losing its rings faster than we thought, the answer is nuanced. Yes, faster than early assumptions suggested, but still incredibly slow by human standards. We are not witnessing a collapse. We are observing a gradual evolution, a majestic structure slowly transforming. And that transformation reminds us of a fundamental truth about the universe. Even the most beautiful things are temporary. In the next part, we will step even further back, comparing Saturn's rings to those of other planets and exploring whether ring systems across the universe might all be fleeting, transient phenomena rather than permanent cosmic features. If Saturn's rings are temporary, then we have to ask a bigger question. Are all planetary rings temporary? Because Saturn is not alone. Jupiter has rings, Uranus has rings, Neptune has rings. Even small bodies in the outer solar system, like the Centaur object Chariklo, have been found to possess narrow ring systems. Rings, it turns out, are not rare. They are simply usually faint. Saturn's rings dominate our imagination because they are massive, bright, and structured. But in a broader cosmic sense, ring systems appear to be natural byproducts of gravitational systems, and that realization changes the entire conversation. If rings are common but usually subtle, then Saturn may not be exceptional because it has rings. It may be exceptional because we are seeing it during a particularly dramatic phase. Let's compare. Jupiter's rings are thin and dusty. They were discovered only in 1979 by the Voyager spacecraft. From Earth, they are invisible through ordinary telescopes. Why are they so faint? Because they are composed mostly of small dust particles, likely generated by micrometeoroid impacts on Jupiter's inner moons. The dust is constantly replenished, but it is also constantly lost. Jupiter's ring system exists in a steady state, thin, dynamic, and relatively fragile. Now consider Uranus. Uranus has narrow, dark rings. Unlike Saturn's bright, icy rings, Uranus's rings are composed of darker material. They are thin and sharply defined, likely maintained by shepherd moons. They are not massive enough to dominate the planet's appearance. Neptune's rings are even stranger. They are clumpy, incomplete arcs rather than full continuous bands. Their structure suggests gravitational confinement by small moons. All of these ring systems share a key feature. They are not ancient, immutable structures. They are dynamic. They are evolving. They are shaped by collisions, resonances, and electromagnetic interactions. Saturn's rings are simply the most massive and reflective example, which leads to an intriguing possibility. Perhaps giant planets frequently cycle through ring phases. A moon drifts inward. It crosses the Roche limit. It shatters. Rings form. Over tens or hundreds of millions of years, the rings thin. They fade. Eventually, they disappear. And later, another moon might repeat the process. If this is true, then Saturn's current ring system may not be its first. It may not be its last. Planetary systems evolve on billion-year timescales. Moons migrate, orbits shift, resonances build and break. There is no reason to assume Saturn has experienced only one catastrophic event in 4.5 billion years. Perhaps it has worn multiple crowns, and we are seeing only the latest. There is another layer to this comparison: exoplanets. In recent years, astronomers have detected thousands of planets orbiting other stars. Some of these planets show unusual light curves, brightness patterns that hint at possible ring systems. One famous example is J1407b, sometimes called Super Saturn. Observations suggest it may possess a massive ring system far larger than Saturn's. If confirmed, it would demonstrate that ring systems can be enormous, but likely temporary. The formation and destruction of rings may be common across the galaxy, which reframes our question: Instead of asking whether Saturn is losing its rings faster than we thought, we might ask, is ring loss simply part of the natural life cycle of giant planets? The evidence increasingly suggests yes. Rings form from debris. Debris spreads, material is lost, the system evolves. Even Saturn's current rings are not uniform in age or structure. Some regions are denser, some are thinner, some may contain embedded moonlets forming slowly from accumulated material. There is even speculation that ring particles might occasionally coalesce into small moons, only to be torn apart again by tidal forces, a continuous cycle of formation and destruction. In that context, Saturn's rings are not a static object. They are a process, a transient arrangement of matter constantly reshaped by physics. And if they are temporary, then we are witnessing a rare aesthetic moment. Consider this. If intelligent observers existed around Uranus during a hypothetical past ring-rich phase, they might have considered Uranus the most beautiful planet. But today, Uranus's rings are faint. Perhaps Saturn once had faint rings too. Perhaps in the distant future, it will again. What we call iconic may simply be timing. There's also an observational bias. Saturn's rings are bright and reflective because they are composed mostly of water ice. That ice reflects sunlight efficiently. If the rings gradually accumulate more dust over time, they will darken. A darker ring system becomes harder to see. Even if material remains in orbit, its visual prominence declines. So disappearance does not necessarily mean total absence of debris. It may simply mean reduced visibility. From Earth, a faint ring system around Saturn might go unnoticed without advanced telescopes. Thus, the rings might disappear long before the last particle falls into Saturn. This nuance matters. When we imagine Saturn without rings, we picture emptiness, but in reality, the transition would likely be gradual. Bright rings, thinner rings, faint rings, diffuse halo, then nearly nothing. And during that entire process, Saturn itself remains largely unchanged. Storms rage in its atmosphere. Its magnetic field persists, its moons orbit. The loss of rings is not a planetary death. It is a cosmetic transformation, but aesthetics influence perception. Saturn's rings inspired centuries of observation and wonder. Without them, perhaps humanity would have focused more intensely on Jupiter or on other phenomena. Beauty shapes curiosity. Curiosity shapes science. So, in a subtle way, Saturn's temporary ring phase may have influenced human knowledge. It drew telescopes toward it. It sparked imagination. It deepened our understanding of orbital mechanics and gravitational stability. Even its eventual disappearance will teach us something, because tracking the erosion of rings over time provides insight into electromagnetic interactions, plasma physics, and planetary evolution. Saturn becomes a laboratory, a living example of how celestial systems change. And that is perhaps the most important realization. The universe is not static. It is not a museum of fixed objects. It is a dynamic system of evolving structures. Saturn's rings are not an exception. They are evidence of that dynamism. So yes, Saturn is losing its rings, but it is also participating in a broader cosmic pattern: formation, stability, erosion, transformation. In the next part, we will explore what Cassini's final plunge into Saturn revealed about the deeper interaction between the planet and its rings, and whether hidden processes beneath the cloud tops may be accelerating the ring system's fate. In September of 2017, Cassini ended its 13-year mission in a way no spacecraft had ever attempted before. Instead of drifting silently away from Saturn, it dove in. The decision was deliberate. Cassini was running low on fuel. Engineers knew they could no longer guarantee precise control over its orbit, and they did not want to risk contaminating moons like Enceladus or Titan, worlds that may harbor conditions suitable for life. So they chose something extraordinary. They turned Cassini into an instrument of final measurement. In its last months, the spacecraft executed what scientists called the grand finale. It passed through the narrow gap between Saturn's innermost ring and the planet itself, a region no spacecraft had ever explored. It was risky. There could have been debris, undetected particles, large enough to damage instruments, unknown radiation hazards. But Cassini survived each dive, and with every pass, it collected data that would reshape our understanding of Saturn's rings, because flying between the rings and Saturn allowed scientists to measure something critical: gravity. As Cassini passed through the gap, it experienced tiny variations in Saturn's gravitational pull. These subtle changes could be detected through radio signals sent back to Earth. By carefully analyzing those signals, scientists could calculate how much mass existed in the rings. This was crucial. Before Cassini, estimates of ring mass varied significantly. Some models suggested the rings were massive enough to survive much longer. Others hinted they might be lighter and therefore more vulnerable to erosion. Cassini's data leaned toward the lighter side. The rings contain roughly the mass of a small moon, perhaps comparable to Mimas. That sounds substantial, but in planetary terms, it is fragile. A moon-sized amount of material spread into a thin disk over hundreds of thousands of kilometers is not dense. It is exposed, and exposure means vulnerability. But gravity was not the only revelation. As Cassini skimmed closer to Saturn's upper atmosphere, it detected unexpected streams of particles flowing inward from the rings. This was not merely theoretical ring rain anymore. It was direct evidence of material transfer. Cassini's instruments measured charged particles, water-related compounds, and complex molecules entering Saturn's atmosphere. The rate of this transfer suggested that the interaction between rings and planet is not subtle. It is active, it is ongoing, and it is measurable. There was something almost poetic about Cassini's final act. A spacecraft built to study Saturn's rings ended its mission by plunging into the very planet those rings are slowly feeding. As Cassini entered Saturn's atmosphere, friction increased. The spacecraft began to tumble. Instruments transmitted until the last possible moment. Then contact was lost. Cassini became part of Saturn, just like the rings eventually will. That symbolism is difficult to ignore. But beyond symbolism, Cassini revealed deeper layers of complexity. The gravitational measurements also helped scientists refine models of Saturn's interior. Understanding Saturn's internal structure matters, because its gravity influences ring dynamics. Saturn is not a uniform sphere. It is a rapidly rotating gas giant with internal density variations. These variations affect how ring particles orbit. Precise knowledge of Saturn's gravity field allows better modeling of ring stability, and those models reinforce a key conclusion. The rings are not stable on billion-year timescales. They are evolving. Another fascinating discovery involved Saturn's magnetic field. Saturn's magnetic axis is almost perfectly aligned with its rotational axis, more so than any other known planet. This alignment influences how charged particles from the rings move. It may even affect the distribution of ring rain. Understanding this magnetic structure helps refine estimates of erosion rates. The better we understand the field, the more accurately we can project the future of the rings. Yet, even with Cassini's wealth of data, uncertainties remain because the rings are not uniform. The B ring is dense and opaque in places. The C ring is more diffuse. The A ring lies between them, structured but less massive. Each region responds differently to gravitational and electromagnetic forces. Ring rain rates likely vary by region. Mass loss is not evenly distributed. This makes lifespan estimation more complex. It also means the disappearance will not be uniform. Some parts of the rings may fade faster than others. Gaps may widen. Bright regions may thin. Patterns may shift. From Earth, we might first notice subtle changes in brightness long before the rings vanish entirely. Cassini also revealed that ring particles are not just simple ice chunks. They contain complex organic molecules. carbon-based compounds mixed within the ice. These molecules may originate from meteoroid impacts or from Saturn's moons. As ring material falls into Saturn, it alters the chemistry of the upper atmosphere. In effect, the rings are chemically interacting with the planet. The system is not static debris orbiting in isolation. It is a feedback loop. Material leaves the rings and enters Saturn. Saturn's magnetosphere influences ring particle motion. Moons contribute plasma and gravitational perturbations. All of it is interconnected, and Cassini gave us a rare glimpse into that interconnectedness. But perhaps the most profound lesson of Cassini's final mission is this: we were wrong about permanence. For centuries, rings seemed eternal, even after early theoretical work suggested possible instability. The idea of Saturn losing its rings felt abstract. Cassini turned abstraction into measurement. It quantified loss. It measured mass. It provided numbers, and numbers changed narratives. The story shifted from "are the rings temporary" to "how temporary." That shift matters because it reframes Saturn not as a static icon, but as an evolving system caught in transition. And transitions are powerful moments. They are brief, they are dynamic, they are revealing. If we had visited Saturn 1 billion years ago, we might have found no rings. If we visit 1 billion years from now, we may find none again. Cassini happened to arrive during the ringed epoch. That timing feels almost fortunate. We built the technology at the right moment in cosmic history. We sent a machine across billions of kilometers to study a phenomenon that may not exist forever. And we ended that mission by diving into the planet itself, ensuring no contamination, preserving future exploration possibilities. Cassini's legacy is more than data. It is perspective. It reminds us that beauty in the universe is often temporary. It reminds us that even the grandest structures are governed by physics, and it reminds us that change, even at planetary scales, is inevitable. In the next part, we will step beyond Saturn and consider what its fading rings teach us about planetary evolution across the entire solar system, and why transient features may be more common than we once believed. If Saturn's rings are temporary, then Saturn becomes more than just a planet with a fading halo. It becomes a case study, a living example of how planetary systems evolve over time, not in dramatic explosions, but in slow, almost invisible shifts that only reveal themselves through careful observation. And when we widen the lens beyond Saturn, we begin to see something profound. Transient structures may be the rule, not the exception. For most of human history, we treated the solar system as a finished sculpture. The planets were fixed. Their features were permanent. The moon always had its craters. Jupiter always had its bands. Saturn always had its rings. But modern space exploration has dismantled that illusion. Mars once had rivers. Venus may once have had oceans. Earth's continents have rearranged themselves countless times. Even the asteroid belt is not static. It is the remnant of a failed planet formation process that never completed. Now Saturn joins that list. Its rings are not a timeless crown, they are debris. And debris does not last forever. The realization that Saturn's rings are fading forces us to confront a larger truth. Planetary systems are not stable masterpieces. They are ongoing processes. To understand this, we have to think in deep time, over billions of years. Moons migrate, gravitational resonances shift, impacts occur, orbits change. These changes are usually too slow to notice within a human lifetime, but on cosmic timescales, they reshape entire systems. Take Earth's moon as an example. The moon is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. That seems insignificant, but over millions of years it adds up. Hundreds of millions of years from now, the moon will appear smaller in our sky. Solar eclipses will change. Tidal patterns will evolve. Nothing in the Earth-Moon system is truly permanent. The same is true for Saturn's moons. They are migrating outward due to tidal interactions. As they drift, the resonances between them shift. Resonances are not static. They are delicate balances of orbital timing. If that timing changes, stability can collapse. A moon that was once safe may find itself on an unstable trajectory. If it crosses Saturn's Roche limit, destruction follows, which brings us back to rings. Rings may be symptoms of instability. When a moon breaks apart, it forms a ring. When the ring fades, the system appears stable again. But that stability may only last until the next disruption. In this way, Saturn's rings might represent a temporary release of gravitational tension, a system adjusting itself through destruction and reformation. Now expand this idea further. Consider exoplanetary systems. We have discovered planetary systems far more chaotic than our own. Some contain hot Jupiters, gas giants orbiting extremely close to their stars. Others show evidence of planets migrating dramatically inward or outward over time. If planetary migration is common, then ring formation and loss may also be common. The galaxy may be filled with ringed worlds in various stages of evolution, some bright and dramatic, some faint and fading, some newly formed, some long gone. We happen to observe Saturn during its ring-rich era, but cosmic timing is everything. If human civilization had arisen 500 million years earlier, perhaps Saturn's rings would have been even more massive. If it arises 500 million years later, perhaps Saturn will appear bare. The aesthetic of our solar system is not fixed. It is a temporary configuration. This idea challenges a deeply human instinct, the desire for permanence. We like to believe that the night sky is constant, but it is not. Stars evolve, nebulae disperse, galaxies collide, planets change, rings fade. Saturn's rings remind us of that impermanence, but they also offer something else, perspective. Because even though the rings are temporary in cosmic terms, they are effectively eternal compared to human history. If they last another 100 million years, they will outlive every civilization that has ever existed. They are fragile, but not fragile in a human sense. They are fragile in a cosmic sense. That distinction matters. It prevents us from slipping into melodrama. Saturn's rings are not vanishing tomorrow. They are evolving gradually, predictably, according to the laws of physics. And yet the emotional impact remains, because Saturn without rings feels incomplete. Our perception of planetary identity is shaped by appearance. Saturn's identity is inseparable from its halo, but identity in the universe is fluid. If we visited Saturn 2 billion years ago and found it ringless, we would not consider it incomplete. We would consider it normal. The rings are not intrinsic to Saturn's existence. They are transient ornamentation, and that realization extends beyond Saturn. When we look at distant exoplanets and imagine them as static worlds, we are likely oversimplifying. They too are evolving. Moons forming and breaking apart, atmospheres thickening and thinning, magnetic fields strengthening and weakening. The universe is not a gallery of finished paintings. It is an ongoing symphony of change. Saturn's fading rings are one movement in that symphony, a slow diminuendo, a gradual thinning of brilliance, but perhaps not a final note. Because if ring formation can occur once, it can occur again. If moons migrate, if resonances shift, if catastrophic events happen, new rings could form. Saturn's history may include multiple ring cycles. We cannot see that deep into the past, but gravitational physics does not forbid it. In fact, it makes it plausible, which means Saturn's rings are not a singular miracle. They are part of an evolutionary rhythm. Form, shine, fade, repeat, and we happen to live during the shine. In the next part, we will turn toward a final question, not about physics, but about perspective. If Saturn's rings are temporary, what does that teach us about how we see the universe? And how does knowing their fate change the way we look at the night sky? If Saturn's rings are fading, and if we are witnessing only one chapter in a long evolutionary cycle. Then the final question becomes less scientific and more philosophical. What does it mean to know that something so magnificent is temporary? For centuries, Saturn's rings symbolized permanence. They looked like architecture, precise, balanced, symmetrical, a perfect disk around a perfect sphere. When Galileo first saw them, he didn't understand what he was looking at. The rings were too strange. Later, astronomers slowly unraveled their structure. But even then, the idea of change was distant. The sky was assumed to be stable. But modern astronomy has dismantled that illusion piece by piece. We now know that stars are born, live and die. We know galaxies collide. We know black holes merge. And now we know that Saturn's rings, perhaps the most visually iconic structure in our solar system, are not eternal. They are temporary arrangements of ice and gravity. And that knowledge transforms the way we look at them. Because when something is permanent, it becomes background. But when something is temporary, it becomes precious. If Saturn's rings will vanish in 100 million years, then we are living during a rare window in cosmic time. Not rare in a statistical sense perhaps, but rare in the sense that we are here to see them. Humanity exists during Saturn's ringed era. That coincidence carries weight because the universe does not promise stability. It does not freeze itself in a configuration convenient for observers. It evolves, regardless of whether anyone is watching. And yet here we are, watching, studying, measuring, understanding. Cassini arrived at Saturn during this ring phase. If it had been launched 1 billion years ago, it would have found something very different. If it were launched 1 billion years in the future, it might find no rings at all. The mission happened at exactly the right moment in planetary history. That is not destiny, it is timing. And timing shapes discovery. But there is a deeper lesson here. We often think of planetary systems as static diagrams in textbooks. Neat circles, fixed labels, permanent features. Saturn with rings, Jupiter with bands, Earth with a moon. But the reality is dynamic. The Earth-Moon system will change, Jupiter's storms will evolve, Saturn's rings will fade. Even the solar system's architecture will shift as the sun ages. The idea of permanence is a human projection. The cosmos operates on longer timelines, and those timelines erase even the most beautiful structures. Yet impermanence does not diminish value. In fact, it enhances it. Consider Earth's own features. The continents we know today will not exist forever. Mountain ranges erode, coastlines shift, ice caps melt and reform. Life evolves. Nothing remains fixed. But that does not make Earth less extraordinary. It makes it dynamic. Saturn is the same. Its rings are not eternal, but they are extraordinary. They are an active laboratory of gravitational physics. They reveal how tidal forces work, how collisions redistribute energy, how electromagnetic fields interact with charged particles. They have taught us about orbital resonance and planetary formation. They are not just decorative, they are informative, and knowing they are temporary adds urgency to that study because it reminds us that observation matters. The universe is not static. If we want to understand it, we must observe it while it exists in its current state. Cassini did exactly that. It arrived during a ring-rich era. It measured mass, it measured ring rain, it dove between planet and rings. It transformed speculation into data, and in doing so, it preserved knowledge of a structure that may not always exist. There is something profound about that. We are not just passive observers. We are chroniclers of cosmic change. We document phenomena that may one day disappear. Saturn's rings will not vanish within our lifetimes, but they will vanish on a timescale meaningful to planetary evolution. And perhaps future astronomers millions of years from now will look back at archived data and see images of Saturn during its brightest ring phase. They will know that once, long ago, Saturn wore a luminous crown, And that crown faded, that perspective reframes the entire question. Is Saturn losing its rings faster than we thought? Yes, faster than we once assumed, but not suddenly, not catastrophically, gradually, predictably, according to physics. And perhaps that is the most important lesson. The universe does not require drama to create change. Change happens quietly, particle by particle, collision by collision, charge by charge. Ring rain falls, material spirals inward, mass diminishes, beauty thins, and the process continues without spectacle. That quiet transformation mirrors so many cosmic processes. Stars exhaust their fuel slowly before collapsing. Galaxies drift toward each other for billions of years before merging. Even black holes grow by gradually accreting matter. Saturn's rings are simply another example of slow evolution, but because they are so visually striking, their evolution feels more personal. They are easy to picture, easy to imagine fading, and that makes their impermanence emotionally resonant. Perhaps that is why the idea unsettles us, because we associate Saturn with stability. We use it as shorthand for permanence, yet Saturn itself is changing, just as everything else is. In the final part, we will step back one last time and consider the full arc of Saturn's ring story, from formation to erosion, and what it ultimately tells us about the nature of cosmic beauty and time. When we trace the story of Saturn's rings from beginning to end, from violent formation to gradual erosion, we begin to see them not as objects, but as chapters, a beginning, a middle, and an eventual ending. The beginning was likely catastrophic, a moon straying too close, a collision shattering an icy body, a sudden redistribution of matter into orbit. In that moment, chaos reigned, fragments flew outward, debris spiraled around Saturn. But chaos did not last. Gravity imposed order, collisions dampened motion, the fragments flattened into a thin disk, and the rings were born. The middle, the era we inhabit, is one of brilliance. The rings are wide and reflective. They dominate Saturn's silhouette. They carve shadows across the cloud tops. They shimmer in telescopic views. They are stable enough to appear permanent, yet dynamic enough to ripple with waves and gaps. This middle chapter has lasted perhaps a few 100 million years, long enough to feel ancient, short enough to be temporary. Now we stand at the threshold of the ending. Not an ending we will personally witness, not a dramatic collapse, but a slow thinning. Cassini revealed that particles are falling inward. Ring rain drizzles down magnetic field lines. Micrometeoroids strike and darken the ice. Collisions grind large chunks into smaller grains. The system is losing mass. Bit by bit, the ending will not arrive with a flash. It will arrive with fading. The B ring will thin, the A ring will lose sharpness. The Cassini division may widen or blur. From afar, Saturn will slowly resemble its siblings, gas giants with faint halos rather than luminous disks. And eventually, the rings may be so diffuse that they are invisible without advanced instruments. That is the full arc: formation, brilliance, erosion. But here is what makes the story extraordinary. We understand it while it is happening. Humanity has existed for an infinitesimal fraction of Saturn's life, yet during that fraction, we have developed the tools to measure its evolution. We have sent spacecraft across billions of kilometers. We have analyzed gravitational fields with astonishing precision. We have detected the invisible snowfall of ice into Saturn's atmosphere. We are aware of the ending before it completes. That awareness is rare in cosmic terms. Most processes in the universe unfold without observers capable of comprehension. But here, in this moment, a species on a small rocky planet understands that a gas giant's rings are temporary. That knowledge adds meaning because it connects us to deep time. When we say Saturn is losing its rings faster than we thought, What we are really saying is this: our assumptions about permanence were wrong. The rings are not eternal architecture. They are transient phenomena governed by physics. And that realization changes how we interpret beauty. Beauty in the universe is not static. It is emergent. It arises from specific conditions: gravity balanced against motion, ice balanced against magnetism, resonances balanced against collisions. When those balances shift, beauty shifts. The rings exist because multiple forces align within a narrow window of parameters. Change any one of those parameters: ring mass, moon positions, magnetospheric strength, and the appearance of Saturn transforms. This is not unique to Saturn. It is true for stars, galaxies, nebulae. The Orion Nebula, for example, is a star-forming region. In a few million years, its gas will disperse. The brilliant clouds will fade. The structure we see today will not persist, yet we do not mourn the future disappearance of Orion. We marvel at it now. Saturn's rings deserve the same perspective. They are a temporary configuration of matter and energy. They exist in this epoch. They will not exist in others, and that does not diminish them. It elevates them because impermanence adds rarity, and rarity adds wonder. But there is another possibility we must acknowledge. What if the rings are not in their final chapter? What if orbital instabilities in the future create new rings? What if Saturn undergoes multiple ring cycles over billions of years? In that case, the rings we see today are not a final act, but one movement in a recurring symphony. The current ring system may fade, a future moon may break apart, new rings may form, perhaps brighter, perhaps darker. Planetary systems are capable of renewal through destruction. This cyclical possibility softens the narrative of loss. Instead of a single fading crown, Saturn becomes a planet that periodically adorns itself with rings. But even if that is true, each ring epoch remains temporary. Each phase has a beginning and an end, which means our observation of this one remains meaningful. We are witnesses to a particular configuration, a particular alignment of forces, a particular chapter in Saturn's evolution, and witnessing matters because knowledge accumulates. Cassini's data will outlive the rings themselves. Future generations, whether human or something else, will know that Saturn once wore bright rings during this era. They will know how they formed, how they eroded, how they interacted with moons and magnetism. They will not have to guess, they will have records. And that preservation of knowledge is perhaps the most enduring thing of all. The rings may fade, but understanding persists. In the final part, we will bring this story together, not as a prediction of doom, but as a meditation on cosmic change, timing, and what it means to observe something magnificent while it still exists. When we first asked the question, is Saturn losing its rings faster than we thought? It sounded like a countdown, like something dramatic was about to happen, like we might look up one night and see a different sky. But the truth is quieter than that. Saturn's rings are not collapsing, they are not shattering, they are not vanishing in an explosion of ice. They are fading, and fading is more powerful than destruction, because fading reminds us of time, not human time, not historical time, but planetary time. The kind of time in which 100 million years can be considered brief. The kind of time in which entire ecosystems on Earth rise and fall between two orbital adjustments of a distant moon. Saturn has existed for 4.5 billion years. During that time, it has likely changed in ways we cannot fully reconstruct. Its moons have migrated. Its magnetic field may have shifted. Its atmosphere has evolved. Its internal structure has cooled, and somewhere within that vast stretch of time, a moon may have wandered too close. Tidal forces may have torn it apart. Ice may have scattered into orbit. Gravity may have shaped that debris into a luminous disk, and the rings were born. That birth may have been violent, but what followed was elegance. A thin plane of ice stretching hundreds of thousands of kilometers, reflecting sunlight across the solar system, a structure so delicate that it appears unreal, so symmetrical that it feels intentional, yet it is entirely natural, a consequence of gravity and motion. And now, particle by particle, that structure is returning to Saturn. Ring rain drifts down magnetic field lines, collisions grind ice into dust, micrometeoroids darken and erode the surface. The rings are not static, they are in transition. We used to believe they might be as old as Saturn itself, billions of years, a permanent feature. But Cassini's measurements shifted that belief. The rings appear younger, hundreds of millions of years old, perhaps with only hundreds of millions of years remaining. In cosmic terms, that is a narrow window. We are living within it. That fact does not make us special in a mystical sense. It makes us fortunate in a scientific one, because we have the technology to observe Saturn during its ringed era. We have telescopes, we have spacecraft, we have data. If intelligent observers had existed before the rings formed, they would have seen a different Saturn. If observers exist long after the rings fade, they will see another version. We happen to see this one, and knowing it is temporary changes how we see it. Impermanence sharpens perception. When something is eternal, it blends into the background of expectation. When something is finite, it becomes vivid. Saturn's rings are not eternal architecture. They are a temporary sculpture made of ice and gravity. That realization does not diminish their beauty, it intensifies it, because beauty shaped by time carries weight. We know the rings are evolving. We know the system is dynamic. We know Saturn's magnetosphere is pulling particles inward. We know the moons are shaping and reshaping the disk. We know the mass is slowly decreasing. And yet when we look at Saturn through a telescope, it still appears serene, unchanging, majestic. There is a lesson in that contrast. The universe often appears stable because change happens slowly, but slow change is still change. Saturn's rings will likely thin. They may fade into a faint halo. They may eventually disappear from casual observation. The planet will remain. Its storms will continue. Its hexagonal jet stream will persist. Its moons will orbit, but its identity in our minds will shift. The ringed Saturn of textbooks and childhood drawings will become a historical phase. And that thought invites perspective, because Saturn is not alone in its evolution. The Sun itself will one day expand into a red giant. Mercury and Venus may be engulfed. Earth's oceans will evaporate. The solar system will transform completely. On those timescales, Saturn's rings are a brief flourish, a decorative arc in a much larger narrative. But brevity does not equal insignificance. A sunrise lasts minutes, a flower blooms for days, a comet streaks across the sky for hours. Temporary phenomena often feel the most powerful. Saturn's rings are a cosmic version of that, a bloom of ice in orbit, and like all blooms, they will eventually fall. But perhaps that is what makes them unforgettable. They exist at the intersection of stability and motion, of permanence and impermanence, of structure and decay. They remind us that even at planetary scales, nothing is frozen in time. Everything is part of a process. When we say Saturn is losing its rings faster than we thought, we are acknowledging that our understanding has evolved. We once imagined permanence. Now we see transition. That shift in understanding is itself part of the story. Science does not freeze knowledge. It refines it. It corrects assumptions. It replaces certainty with deeper insight. Cassini did not make Saturn's rings disappear. It made us aware of their fate, and awareness is powerful because it transforms observation into appreciation. The next time we see Saturn in an image, a pale sphere wrapped in luminous bands, we can look at it differently, not as a static icon, but as a moment in motion, a chapter in progress, a structure slowly evolving. The rings are not ending. They are changing, and change is the constant thread that runs through the universe. From atoms to galaxies, from moons to magnetospheres, from ice particles to planetary atmospheres, Saturn's rings are part of that thread. They formed, they shine, they fade, and in fading, they tell us something essential. Beauty in the cosmos is not permanent. It is emergent. It appears under specific conditions. It persists for a time, and then it transforms. We are here during one of those times, watching, measuring, understanding, and that perhaps is the most extraordinary part of the story.